Welcome to the lecture. In the last lecture, we talked about determinants, and we actually discussed how we can actually calculate determinants. We looked at the covector expansion of calculating the determinants, and then we talked about the properties of determinants that helps us actually to simplify the calculations involved in determinants. And those properties were that if A is a square matrix, if you add multiple of one row to another row, it will not change the determinant of that matrix. So if this operation results in another matrix B, then determinant of B is equal to determinant of A. Now if two rays of A are interchanged to produce B, then determinant of A is nothing but equals determinant of B is nothing but equals to determinant of minus determinant of A. And if one row of A is multiplied by K to produce B, then determinant of B is nothing but equals to K times determinant of A. Okay, now we did some examples to illustrate the effectiveness of these properties, and we said that if A is a triangular matrix, the determinant of A is nothing but the product of the entries on this main diagonal of A. So you can convert a matrix A into a triangular form by using the row operations, and those row operations and its effect is summarized in those properties of determinants. Now similarly, we said that a square matrix A is invertible if and only if a determinant of A is actually equal to 0. We'll talk about invertibility of the matrix, a few portion of that invertibility in this lecture, and hopefully in the coming lecture we'll talk it in length, where we'll say detailed view of the invertibility of the matrix A, right? And at the last, what we discussed was that the column operations, and the last most important thing that we talked about was that if A is n by n matrix, then determinant of A transpose is equal to determinant of A, meaning that the column operations are similar to row operations, and either you carry out row operations on a matrix A, or either you perform column operations on matrix A. It will not change the determinant of that matrix. Okay, and the same set of properties that we discussed before are actually applicable to the column operations as well. Now we look at another property of determinants, which is when two matrices are being multiplied. So let's say if A and B are n by n matrices, then determinant of AB is equals to nothing but determinant of A times determinant of B. Okay, now you can simply start proving that with the 2 by 2 matrix. So 6 1 3 2 the matrix A is a 2 by 2 matrix, and there's a B matrix which is 4 3 1 and 2. So if you multiply A with B, you get an answer as 6 4 24 plus 25. Then you got 6 18 plus 2 is 20, and then you got here 3 4 12 plus 2 is 14, and again this one has 13, right? Now if you do that determinant, calculate the determinant of AB, that becomes 25 into 13 minus 20 into 14, that becomes 325 minus 280, that becomes 45, right? Now so this is determinant of AB. Now if you find the determinant of a here, determinant of a here is nothing but equals to 18 minus 3, that will be 15, and this is determinant of b is equals to 5, is equals to 8 minus 3, that will be 5, right? Now determinant of 2 into 6, 12, 12 minus 3 is, so that will be 12 minus 3, that will be 9, sorry, and that is determinant of AB is equals to determinant of A times determinant of B, that is 45 is equals to 9 into 5, okay, so 45 is equals to 45. So so if they are product of two matrices, you can say the determinant of AB is nothing but the multiplication of the individual determinants of these matrices. Now, but one thing that you have to remember is that determinant of A plus B is not equal to determinant of A into plus determinant of B. Okay? Actually, this is in almost all the cases, right? It is not true, right? Generally, it's not true. So this is not true. Generally, it's not true. There may be some specific cases it may be true, but most of the time it is not true. And we'll discuss the cases in which they become true. But but let's talk about another important property, which is the linearity property of determinant function. Now, now this is a very, very important property. Now, if let's say A is an n cross n matrix, so we can actually consider determinant of A as a function of n column vectors in A. So, determinant of A you can think of as determinant of you can think this one as A1 up to AN, right? So you can now think of determinant of A as a function of A1 up to A2, A3 and AN, right? So for example, if I fix all the columns, right, I mean nothing will change, right? But let's say if I fix n minus 1 columns and change a single column, it means, let's say if I replace this A as something like this, which is A1 up to AJ minus 1 x and AJ plus 1 up to AN. So what I have done here is this is because you know this is n columns. Now I have fixed all the columns, n minus 1 columns, and I have replaced one of the columns, which is the jth column here, by a vector x, right? So to illustrate this, let's say as an example, A was 1 3 4 2 5 9 8 7 3, right? So this is A1, this is A2, this is A3. Now I can actually replace and say x is equals to 5 2 4, right? So if I can say this, I can write this as something like A is equals to like this 1 3 4 and again 5 2 4. Now this is x, right? And 8 7 3. Now which is the form which is a1 and I've written as x, and this is now a3. So I've replaced the second column of that A matrix with x. Okay, so now if I do that, right, so this determinant actually becomes a function of x, right? Because previous determinant was for these vector will have a certain value, but once I replace one of the columns with x, right, it means this determinant will effectively change. Now, so it means I can actually write this as I'm just slightly abuse of the notation. I can write in t of x, right, which is defining as determinant of a1 aj minus 1 and x aj plus 1 an. So it means the determinant will become this function of x, right, and that is called t of x, right? All other columns will remain the same of this A matrix. Only one of the columns, which is the jth column in this scenario, will be replaced by x. Now the column that I'm replacing, right, with the variable x, now this determinant will become as a function of x, because everything will remain the same, but this will every other column except the jth column will remain the same. Only the jth column will be replaced by x. So it means if x can take different values, the determinant will have different values. Okay, now this is actually the linearity property of determinant function. Now if I say now t of, if I multiply this t by cx, right, then this is nothing becomes c dx, because remember this, the third property of the determinant, that, or the c property of the determinant, that if you multiply a row or a column, right, with a scalar quantity k, then determinant becomes k times determinant of a, right? So if I scale any column by c, right, the determinant becomes c times t of x. Now in this case, now this is the first property. Now the second property here is where, remember, the c is a scalar quantity, right? C is scalar and x is in Rn, right? Now if I say there t of u plus v, right, so if x is a combination of two vectors u and v, right, so I can actually separate them out as t of u plus t of v, because if, let's say, x here is u plus v, right, so aj plus 1 an, right, so I can actually separate out this one, and I can write this as the transformation t of u plus t of v, right? So remember this, u and v belongs to Rn. Okay, actually to prove this, right, that you can write this as t of u plus v as t of u plus t of v, right? What you can now do is actually you can prove that from the perspective that if we do the cofactor expansion from the jth column, it means u plus v vector, right? And this is actually also an assignment for you. So if you do a cofactor expansion from u plus v, you can actually come to this form right here, t of u plus t of v. So this is your assignment, right? And to be exact, this is the problem. So exercise number 43, okay, in exercise 3.2. Okay, so you have to take this as an assignment, and what you do is so I'll explain it to you. So this is the matrix here, right? This is transformation here. So what you have to do is to separate out in a form like this as T of u plus T of v. It means if T of u plus v is determinant of a1 up to aj minus 1 u plus v into aj plus 1 en, right? You have to write that's determinant of a1 aj minus 1 u aj plus 1 en and plus determinant of a1 to aj minus 1 and then v aj plus 1 up to an, right? So you can actually, you have to prove this, that this is equal to this thing here, right? Now to prove that, as I told you, you have to basically do the cofactor expansion from u plus v, and this is your assignment that that you need to submit, right? Okay, so coming back to the point that we were making the last lecture about the dependency of the vectors in a matrix A, to ensure that if the determinant exists or not, right? So we are going to do an example in which we use a determinant to decide if v1, v2, v3 are linearly independent vectors. Now, classically what we used to do, if you remember in the last lecture, was we used to write v1, v2 and v3 in a form like this, and try to find the solution of a solution, right? Now since we know that linear independent vectors only has the trivial solution, they don't have any non-trivial solution, right? So we used to find out if there's another other non-trivial solution exists for these kind of vectors. But if it is, right, so they are dependent. If only trivial solution exists, we say okay, they are independent vectors, right? But there's another method through which we can actually determine their dependency, and which is by using the determinant. So it means determinant v1, v2 and v3, if you find out that in this case becomes 5 minus 7 9, minus 3 3 and minus 5 2 minus 7 and 5, right? Now so we take the term, we try to find the determinant of this matrix, which is built up by v1, v2 and v3, right? Now if I do that, right, so I can actually do some kind of row operations in which I can add row 1, I can add to row 2, so that becomes here becomes 5 minus 3 2 minus 2 0, and then you have minus 5 and 9 and minus 5 and 5, right? Now I can now actually do the expansion across this thing here, and when I do that, right, that becomes cofactor expansion minus 3 times again this is minus 3 because minus 1 into 1 plus 2, so this is 1 plus 2, and again you have minus 2 minus 5 9 and 5, and you have minus 5 again coming from here. So this minus coming from, actually I should write this as 3 2, and this actually comes out to be 5 2 minus 2 minus 5, right? When you calculate that, you will find out this comes out to be 3 times 35 plus 5 times minus 21, which comes out to be 0, right? So the determinant of this v1, v2 and v3 equal to 0 and now since this determinant is 0, it means they are actually linearly dependent vectors. So they are v1, we can write that v1, v2 and v3 are linearly dependent. And we can actually show that as well, right, by using the classical operations of row elimination. Now the next topic that we're going to discuss, which is quite in line with the determinant that we have just discussed, are the Kramer rules. So Kramer rule is one of the methods to solve system of linear equations, and actually the Kramer rule is needed in a variety of theoretical calculations. For instance, we can use it to solve ax is equals to b, the classical system of linear equation problem. Now so in generally it is quite an old method, and it's quite useful when you are calculating 2 by 2, when a is in the dimension of 2 by 2 or 3 by 3. Now if a gets a much higher order, let's say 4 by 4, 5 by 5, Kramer now is not very useful method to solve for the value of x, right? So so coming back to the problem of Kramer rule, the thing here is that since we just discussed the linear transformation of determinants, which is t of x, remember this is nothing but determinant of a1 up to a of j minus 1 x, a of j plus 1 up to a n, right? Now we can define ai b as a matrix in which I replace the ith column of a with b, right? So we have got matrix ax is equals to b. We are trying to find the value of x, for which when I multiply with a will fetch me b, right? So what I do is in this matrix A, which is can be thought of vectors like that, right? I replace this b which is given to me, and I place this b in the ith column of A. So if there was somewhere a I here, right, I replace this ith column of A with b, right? Now the Kramer rule says that xi, if A is invertible, A is an invertible matrix, and remember that for invertible matrix, determinant of A should not be equal to 0. Okay. Now so for any b in Rn, for any b that is in Rn, the unique solution x of ax is equals to b is can be calculated like that: x is equals to determinant of aib divided by determinant of a. So I is equals to 1 to n because there are n elements. Now so what we have done here, to summarize, we have this matrix A, which is a1 to an, right? And what we want to do is to solve for x. A is given and b is given, right? So what we do here is we replace the ith column, right, of this matrix A with b, and we use that aib to calculate determinant, to calculate the value of x of I. Okay. Now to prove that thing here, so let's say A is composed of this a1 up to an, and I is an identity matrix, which is we know its diagonal entries are 0, and diagonal entries are 1, and all other entries are 0. So E1, you can think of E2 up to En. So E1 actually is 1 0 0, and right 0 here. En is nothing but equals to 0 0, and this is 1 here. Okay, now to prove that, so by definition, if ax is equals to b, right, so if I multiply this with a times I of x, it means the identity, this identity matrix, if I replace the ith column of this identity matrix with x, right, so that it means I can write this as a times e1 x and en. So of course this is the ith column. It means this ith row entry is 1, and the rest of them are 0. Okay, now now from the multiplication point of view, I can write this as a times e1, a times x, and this is en, right, a times en. Now we know for that ax is equal nothing but equals to b, so I can write this as a e1 b and a en, right. Now this is nothing but equals to, we know that ae1 is nothing but equals to your thing here as a1, right, and this is b, and this is your an, right. How is that possible that ae1 is equals to a1? You can think of this as a1 up to an, a as this, right, this is your a, e1 we know that is nothing but 1 0 0 0 0 here. So this is actually a1 being multiplied by 1 here, all the remaining terms are multiplied by 0, right, so u plus 0 plus 0 plus 0, and there will be n minus 0. So what answer you get here is a1. So this term, that's why this term is equals to a1. Okay, so a times e1 is a1, so on and so forth, right. So this is nothing but equals to, as we have just defined, is nothing but equals to ai times b. That means same in the ith column here, so a times ix is equals to a times b. Now if you take the determinant of this on both sides, you get determinant of a times I of x is determinant of a times I of b. Now because we know that determinant of a b matrix is determinant of a into determinant of b, this is determinant of a, and this is your determinant of ix is equals to determinant of ai b, right. Now what is determinant of aix, right? So determinant of iix is nothing but equals to simply xi. So this becomes xi is determinant of ai b divided by determinant of a. See, this is ix, right? So if you replace this by x here, right, so x1, so x is nothing but equals to x1 x2 to xn, right. Remember this determinant of ix will be, if I write this as, this will be 1 0 0, and let's say the ith column here is x1 x2 x3, and somewhere between will be x I, and that will be here, and of course that will be xi, sorry, and that will be xn, right, and that will be 0 0, and this is 1 here, this will be 0. Now since it is a sort of triangular matrix, not completely, but the thing here is all the remaining terms that will be on the diagonal will actually determine the determinant of I of x, right? All the remaining cofactor expansion will come out as 0, right? So this will determinant of IIx is equals to xi. Okay, so xi is determinant of AIB divided by determinant of A. Okay. Now let's do an example to solve this, to use this Cramer rule to solve a system linear equation, which is, let's say, 3x1 minus 2x2 is equals to 6 and minus 5x1 plus 4x2 is equals to 8. Okay, so now for that, A becomes 3 minus 2 minus 5 and 4. X is equals to x1 and x2, b is equals to 6 and 8. Remember this, the formula is xi is determinant of AIB divided by determinant of A, right? So let's find determinant of A first, because that is required in all of the calculations, right? So 4 times 8 plus 10, so 8 minus 10, it becomes minus 2. So determinant of A is 4 3 12 and minus 2 becomes 2. Okay, now now AIB, so there are two values. So for x1 I can write x1 is equal to determinant of A1B, right, and divide by 2. So what is A1B? A1B, I replace the first column of matrix A with B. So this I can write this as determinant of, replacing first column with B, becomes 6 8 minus 2 4 divided by 2, right? So in this case, determinant is x1 is becomes 24 plus 16, that will be 40, divided by 2. In this case, that becomes out 20. Similarly, if I do x2, so it means this is determinant of A to B divided by 2. Now A to B is, remember, this second row has to replace with, second column has to replace with B. So that is determinant of, that becomes 3 minus 5, and this is your second column of A. So that you have to replace with that with B. So B is 6 8 again here. So you write 6 8 here. Okay. And divide by 2, so that comes out to be 24 plus 30, that out to be 54, so it answer becomes 27. So x1 as 20 and x2 as 27. Okay, so now there are a lot of engineering applications for Cramer rule. One of them is if you're studying ODE, right, ordinary differential equations, and we are using probably you will be using Laplace transform to solve this system of linear equations using a system of differential or dynamical system and solve the states. So in this case, you normally use Laplace transforms, and this approach converts an appropriate system linear differential equation to a system of linear algebraic equations whose coefficients involve a parameter, right? So let's do an example to demonstrate how Cramer rule can be used to actually find out the solution of that differential equation. Okay, now let's say we have equation which is 3s times x1 minus x2 is equals to 4 and minus 6x1 plus s times x2 is equals to 1. So in this case, the A matrix will become again here as 3s minus 2 minus 6 s, and your x is again x1 and x2, your b is 4 and 1, right? So your AIB will become 4 1 minus 2s A1b, sorry, and A2b will become you replace the second one with that, so it becomes 3s minus 6, 4 and 1, right? Determinant of A is quite simple, is 3s square, and you got minus 12, right? So it is 3 times a square minus b square, s minus 4, right? Now x1 will become this determinant of a1b, right? Determinant of a, that is 4s plus 2, right, divided by 3 into s plus 4 into s minus 4, and again x2 will become similarly determinant of a to b divided by determinant of a, that becomes s plus a divided by s plus 2 into s minus 2. Okay, now the Kramer-Rao actually rule can be used to find the inverse of a matrix, right? Now you really have to pay attention to this math that I'm going to do now, right? Because it is quite involved, and once you are able to comprehend this math, I think you'll be able to solve the problem with quite ease, and it will definitely help you in calculations of inverses as well. Okay, now remember this. First thing that you have to remember is that a time a inverse is I, right? So if I say this, right, and I is actually remember this is E1, E2 up to En. Now it's an identity matrix, and as I already explained to you, E1 is nothing but equals to 1 0 0 0 0, and E2 is nothing but equals to 0 1 0 0, and of course En is equals to 0 0 0 0 1, right? Now so if I say this, that if the jth column of A inverse, right? So jth column of A inverse is x, right? then I can say A inverse time x is nothing but equals to Ej, right? X is the jth column of A inverse, right? Sorry, my bad. If x is the jth column of A inverse, right here, then if I multiply with A, I will actually have this the column of an identity matrix, a jth column of identity matrix. Okay, because remember this A time A inverse is I, so I can think of this if I multiply with A with A inverse, right? So A inverse has certain amount of columns, so let's say U1, U2 to UN, right? Now if I say any of that column is X, right? Okay, this is in this case the jth column, right? So what I'll get here is A times U1, A times U2, sometimes A times X, and A times UN, right? Now since U1, U2, UN are the columns of A inverse, right? So this will generally produce E1, this will produce E2, this will produce E J, and this will produce En. Okay, so it means AX will be equals to EJ, if X is the jth column of A inverse, right? Now in this case you can think of now this as a system of linear equation. So if X is the jth column of A inverse, finding X actually gives me the value of the jth column of A inverse. Okay, so if I solve this X using Kramer rule, so x1 will give me the first value of the jth column, x2 will give me the second value of the jth column, x3 will give me the third value of the jth column. So in this case, so if I'm solving for the ith entry of X, right, so I can write this as x I j, say for example. Okay, right, now X is the element of ith element of the jth column of A inverse, right? So x ij means the ith element or ith row, you can actually say that, of the jth column of A inverse, right? So you can say xij or in general say ij entry of A inverse is actually equals to xi equals to, now because it's a small linear equation, remember that the determinant of, what you have to do is replace ai with ej, right, and determinant of A. Just look at the resemblance of the Kramer rule, that ax equals to b, right? So xi is equals to determinant of aib divided by determinant of A. Now, so in this case, what I have to do here is I have to find the ith entry on that column. So this is the column here. So this is first entry, second entry, third entry, fourth entry. So first entry, ith entry of that, I have to replace the ith column of A with the jth identity matrix column. Okay, now it has to be divided by determinant of A, right? To give you an example, say so this is, let's say, is A, which is a, let's say, 3 by 3 matrix, A1 2 A1 3 A 2 1 A2 2 A2 3 A 3 1 A 3 2 and A 3 3, right? Now, and remember this is the entry matrix for 3 by 3 identity matrix, 1 0 0 0 1 0 0 0 1, right? So this is your E1, this is your E2, this is your E3. Okay, now this is your A1, this is your A2, this is your A3. Okay, now so let's say if I'm interested in I'm looking at X, let's set J is equal to 2. So it means so the second column X is so X is the jth column. It means the second column of A inverse. Let's say X is the second column of A inverse, right? Which we don't know actually, because what we know is to find this A inverse. We are on a quest to find A inverse, right? So now so if X is the second column here of A inverse, right? Now so it means there is a kind of situation here in which if I multiply this matrix A with A11, A12, A13, A21, A22, A23, A31, A32, A33 with the X right, x1, x2 and x3, which is actually the jth column here, right? So to be precise, I can actually write this one as x1 2 x2 2 x3 2. So okay, now this is equals to, should be equals to, so because the second column, right, so that should produce the second column in the identity matrix, which is nothing but equals to 0 1 and 0. Okay, right. Now since we have developed that, okay, now to find out x12, right, so remember this is the equation in ax is equals to b, right? So like the previous example here, what you can say that x12 in this case is nothing but equals to, what you do here is you replace that row, the one that b here, with that ith entry. So it means what I'll do here is, since I'm talking about the first element of x12, which is I equals to 1, I'm actually trying to say here as like this, which is 0 1 0, right, a12 a13 a22 a23 a32 and a33, and what I'll take is the determinant of that matrix divided by the determinant of a, right? Remember this, the formula of a Cramer rule, there was x of I is determinant of aib divided by determinant of a, right? And it was ax equals to b. Now compare this ax equals to b with this one. Right here. Okay. Now so this is how you're going to proceed. So if I'm trying to find x22, so that will be, I replace the second one here, so determinant of a11 a21 a31. Now you replace this 0 1 0 a13 a23 a33 divided by determinant of a. Similarly, the third one I will write x33 is equals to determinant of a11 a21 a31 a12 a22 a32 0 1 and 0 divided by determinant of a, right? So that is how you're going to proceed. So it means now what you have done here is we were able to find out, once we solved this, we were able to find out the jth column of A inverse, right? So if this was A inverse and x was the jth column, we don't know rest about any other column, so it means I am actually finding out 1 1, in this case 3 by 3 matrix, 1 2 x 2 2 and x 3 3, right? So the thing here, you start with j is equals to 1, j is equals to 2, j is equals to 3, so it means recursively you can actually find out all the values of A inverse. Okay, so now in general, so since I hope that you have understood all this calculations by now, right? So it means I can actually write this determinant, which is now this equation, which is now you've understood this one here, determinant of ai ej. So I can write this as determinant of ai ej is nothing but equals to -1 times I plus j into determinant of a ji, which is equals to cji. Okay, now you can see here from that calculation we just did, right, that determinant of ai ej, that means replacing the ith column of ai with the jth column of the entity matrix. If I do that, right, So I have, like, for 3 by 3 matrix, I have a form like this. Okay, here, right? Now if I do the cofactor expansion of this AIEJ, so this is actually, what I can say here is A1 E2, right? So it may have to find determinant of A1 E2 is actually can say determinant of A1 sorry, A2 E2. This is nothing but determinant of A3 E2, right? So these are the three things here. Now if I do the cofactor expansion on that one, right? Now, so I can write this as to find the determinant. So I can write this as determinant of AI, replacing ith row of the matrix A with the jth column of the identity matrix. I can actually write this as minus 1 times I plus j, and determinant of A, j, and I, right? And it is quite see, it's quite simple, because from here you can actually see that for any scenario, right? So for this is if you look at the so I'll just demonstrate it here. So for example, if I expand it by this column here, so this what I'll get here is I remove this and remove this here, right? So so what I'll get here is A12. So let's do for the first one. So it's in determinant of A1 E2 is nothing but equals to 1 times, sorry, 1 into minus 1 times 1 plus 2 into your A12 A13 A32 and A33, right? Okay, how should I think I should write it more in the center, but anyways, determinant of A1 E2 is equals to minus 1 into 1 plus 2 A12 A13 sorry, A32 and A33. So in the normal circumstances, what do you think this cofactor comes from, right? If in normal circumstances of a matrix A, which is given over here, right? So this is the cofactor expansion of from this is a cofactor expansion from which point do you think? Can you see that? This is a cofactor expansion of C to 1, right? So which is nothing but equals to minus 1 plus 2 A12 A13 A32 and A33. Now this is opposite of how we are dealing with here in this scenario, right? This is the expansion of C to 1, but in this case I have this ith column replaced by the jth column of identity matrix, so which is equals to C to I, right? So here I have the jth column and ith column, or ith entry in this case, to find out xi. So ith entry or ith entry of the jth column, when we're going to find out by replacing the second column, results in cji. See, this is cj, second column, and the first. I mean, you can find it out for the other one as well, right? So for example, I can write for determinant of A3 E2, right, which can be used to find x33, right? So if I do that, right, so you will see that this is nothing but A3 E2 is here. A3 E2 is expansion by from this side here, this comes out to be minus 1 into 3 plus 2, and again you will have a11, a12, a31 and a32. Now this is, in a conventional setup, this is a cofactor expansion of C3 or 2 3, sorry. C23, if you look for it from here, is if A matrix is given by this thing here. I'm writing it again for you to understand this bit. Now this cofactor expansion actually comes from 2 3, right? So which is C23, right? So it is kind of opposite from the conventional perspective cofactor expansion that you see from here, C23. Okay, now so from here, the determinant of aij is nothing but equals to minus of I plus j, determinant of ji and cji. Okay, so I can expand this in a form like that, which is quite easily comprehensivable. C21, Cn1, this C12, C22, and you got here Cn2, and here you got C1n, C2n, and again you have Cnn. Okay, now this is called, if you recall that, it's called adjunct or adjoint of A, right? This is called adjoint of A. Okay, now so let's do an example to explain what we have just did, right? So let's try to find inverse of matrix A, which is 2 1 1 1 minus 1 4 3 1 and minus 2, right? Now it means looking at this formula, so you can find out C11, which is equals to, we'll always have a plus sign, remember this, because 1 plus 1 is minus 1 square. This will be minus 1 1 4 minus 2, and that will be, comes out to be minus 2. Similarly, C21 is equals to minus 1. C21 is second row in the first column. 1 3 4 minus 2, 1 3 4 minus 2, and because this is minus 1 2 plus 1, that becomes 14. C31 is equals to plus 1 3 minus 1 1 is equals to 4. Similarly, C12 is minus 1 1 1 minus 2 is equals to 3. C22 is equals to plus 2 3 1 minus 2 is equals to minus 7. C32 is equals to minus 2 3 1 1 equals to 1. Similarly, C13 is equals to plus here 1 minus 1 1 4, and that is equals to 5. Similarly, C21 2 3, sorry, my bad, minus 2 1 1 4 is equals to minus 7, and similarly C33 is equals to plus 2 1 1 minus 1, right? So we know the determinant of A is equals to 1 over 14. Determinant of A comes out to be 14, and so adjoint of A is nothing but equals to, we know that from that formula, this is C11 C12, so that comes out to be minus 2, right? And second one is 14, and you got here 4 3 minus 7 1 5 minus 7 minus 3. Now you can see here conventionally this is, see, you go first row second column, right? So if you're looking at first row second column, this entry should be C12, but in the case of cofactor, because of this thing here, and as I explained you earlier how this thing is coming out, that it has switched positions across the diagonal. Okay, so this is the diagonal, so it means these actually cofactors have switched positions. Previously, in a normal case, when you're trying to find the determinant using cofactor expansion, this term is C12, but in the case of when you're trying to find the inverse, C12 doesn't come here, it actually goes over here. So actually all the terms actually switch over the diagonal. Okay, same goes here, right? So in this case C11 is minus 2, but I put it here. C12 is 3, which is coming instead of here, it's coming here, right? Now similarly C13 conventionally it should be on that side, but it is now on the other side, which is 4, which is C31. Okay, now so the inverse will become, now we know that it is 1 over determinant of A into adjoint of A. So in this case this is 1 over 14 and minus 2 3 5 14 minus 7 again minus 7 I think, and 4 1 minus 3. Okay, I hope so this is how actually you calculate inverse for matrix. Now next topic that I want to deal with is the physical significance of determinants. Okay, physical significance of determinants. Okay. And this is a topic I think we'll discuss in the next lecture, because it will be much more difficult for you to comprehend more than 1 hour lecture, and especially an online lecture. So in the next lecture probably we'll talk about physical significance of determinants, and then we can move on to the more detailed analysis of vector spaces. So उम्मीद है अब तक कि आपको जो समझाया गया है वो समझ आया होगा, right? The thing here is that you have to really practice this maths, otherwise तो बहुत मुश्किल हो जाएगा इसको आपके लिए कवर करना, right? So I'm putting up another assignment for this course for this chapter, ताकि आप जो है उसको जो है वो बेहतर तरीके से समझ सकें, और जितनी आप बेहतर है कि अगर आप कितने क्वेश्चन सॉल्व करेंगे एट द एंड ऑफ एक्सरसाइज, राइट, तो उतना बेहतर होगा आपके लिए, ठीक है ना? इफ़ यू हैव एनी क्वेश्चंस, कोई क्वेश्चन है आपका, कोई और प्रॉब्लम है, तो बट आई वुड रिकमेंड कि आप कमेंट जो है अपना यूट्यूब के जो चैनल की जो मैं लिंक शेयर करूँगा उस पर रख दें, या फिर आप कैनवस भी पूछ सकते हैं, और अगर आप चाहते हैं इंटरेक्ट करना तो वी कैन हैव यू कैन ट्राई अरेंज अ जूम कॉल इफ़ यू वांट टू, और या व्हाट्सएप कॉल, व्हाटएवर सूट्स यू गाइस। मेजॉरिटी अब अगर आपस में आप डिस्कस कर लें, आई एम ओके विद अ जूम कॉल, और हैंग आउट कॉल भी ठीक है मेरे ख्याल से, दैट वुड बी ऑलराइट एज वेल। प्लीज़ डू लेट मी नो कोई इश्यूज़ हैं, कोई प्रॉब्लम्स हैं समझने के लिहाज से, या तो आई विल बी मोर देन हैप्पी टू हेल्प। ठीक है, थैंक यू जी, अल्लाह हाफ़िज़।